Excellent. Thank you. All right. Excellent. Thank you. Wow. You guys are fast. Wow. Okay. Damage seems minimal. Awesome. Awesome. Wow. It's amazing. What a world we're living in. Oh, remember that time when virus we learned? Okay. Awesome. You guys are, wow. I have to, I feel one problem with this Excel. I feel bad that we haven't had like a get to know each other class. It does seem like you people are worth knowing, but and I know you go, all of you go to like colleges from everywhere, which is cool. One of you even goes to this crazy place called Williams, which used to beat my college in football all the time, but then they changed the name of football to soccer or something. Okay, wow, you guys are back. Thank you very much. Okay, so first of all, I think we're recording now. Yes, we are recording. So I will send you the PDF of everything we've done so far, without a doubt. But I guess there won't be a recording of that first part, for good or for bad. I'll try to summarize it. We now do have breakout rooms again, which is good. But I won't put you in now because maybe they're questionable and maybe we don't have time now. I'm going to assume that in all this shenanigans, I'm not really going to assume this, but I'm going to just act like you got the derivatives that I was asking for. Okay, sorry. Okay, right, so I'm just going to do the derivatives. Okay. Oh, whoa, ha! That's not what I meant to do. Okay, sorry, hold on. We'll be right there. I'm about to, okay, it's totally not, sorry, that tells you something about my family. That is so personal and private. I'm so embarrassed. Just kidding. But sorry, that is not what I meant to do. But I do recommend that program. What? It's happening again. That's so funny. Not really. Okay. I've mentioned, I hope that Gus Johnson video where he makes fun of physics or professors with technology, hilarious. Okay. So this is what I'm saying. To try to redeem myself, I'm saying and it seems to me, so check your work. I would like to solicit your responses, but I feel like now so just check if you did this the same way, if you're getting the same answers. I'm saying if I take one derivative of y with respect to t, then what I will get, okay, I'm going to treat t as the variable. I'm going to pretend that x is a constant. Like I'm not pretending, I'm holding x constant, which is, by the way, just like lab 3, you pick, it's like picking a spot on, it's like, no. It's like picking some position on the x-axis and watching the movie of a bit of your spring go up and down, right? It's like letting time flow at some given fixed position x that you're holding constant in your mind. Doesn't mean that you think that x isn't varying. It means you're just picking one of its values and holding it, right? So if you did that, then you would get negative y naught omega sine omega t plus kx. Oh yeah, they're gone, right? Yeah, right. Right, one derivative, kind of like the simple harmonic oscillation, right? Like the kx is a constant to us now. It's just like phi to us in this context. So the omega comes out from chain rule. The negative sign comes out because the derivative of cosine is negative sine, right? So that's one derivative with respect to time, and it's partial. So I'm using that partial symbol, right? It's the partial derivative of y with respect to t. Then if I do it again, the partial derivative of y, I mean, the partial second derivative of y with respect to t, or the partial second derivative of y with respect to t, well, chain rule says the omega is going to come out again. Again, x is just going to be treated as constant, and k is already constant. So I still they don't do anything to the chain rule, but the derivative of negative sign is negative cosine. So nothing can mess with that negative sign here, but I get this, right? Okay. So this, it's kind of like what happened when we first were taking derivatives of a harmonic oscillator that had some phase constant. Like, chain rule makes the omega come out, but it doesn't make anything else come out. So like that's our answer. That's our answer for the second derivative with respect to time. Okay. Now I might have to go back to this page in a second, but if I now go again, if same function, I'm looking at the same function, just like you're looking at the same phenomenon in a lab that you took a video of, and then you break up the data from that video into different relationships. And each relationship has its own flavor. It's just like group therapy, except ineffective. Hold on. So again, same function, but now if I want partial y with respect to x, hopefully I'm just writing down what many of you just did for yourselves. So I'm just telling you that you're right. And how often do we really get to hear that during a virus? So if I do one derivative, I'm going to get, now I'm treating t as a variable. I'm treating x, no, I'm just kidding. I'm now treating x as the variable, and I'm treating t as a constant. So omega is already a constant. So omega is not going to come out of this due to chain rule anymore. No, in fact, this time what we're going to have is negative y naught k times sine of blah, 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 of omega t plus k x. This is why the Lord on the 8th day invented the typewriter, excuse me. And by the Lord, of course, I mean the one quark to rule them all. Okay, and then the second derivative, the second partial derivative of y with respect to x is take the derivative again. X is still the variable here. So chain rule will force a k out, but nothing's going to happen to the omega or anything, blah, blah, blah. So I get negative y naught k squared cosine omega t plus kx. All right, I'm going to just rewrite these results on the next page in handwriting that's slightly less axe murderish. So the next page is just going to be a recopy of this so that you can actually write it down. So please indulge. So I'm saying, again, I'll try to make it, if y equals this, which we think it does when we're looking at a wave, then I'm saying this equals and I'm saying this equals, that's an equal sign. And I'm saying this equals that. Okay, this, imagine that what the world really wants is a bunch of accurate physics written as though it were graffiti on the side of a building that no longer existed. Then that's what this would be. Okay, but unfortunately that's not what the world needs. So you probably still can't read this, but I'm saying we got two partial derivatives of the same function, two second partial derivatives, one with respect to time, the other with respect to space. Again, why would I even do this? Because I'm a physicist who knows that all the action is in second derivatives, like because F equals ma. That's why I'm doing this. And I'm hoping to find something. And maybe I'm also doing this because I've done a bunch of other things already and they didn't get me anywhere. So I threw them in the garbage and I didn't tell anybody about it, and they didn't get published in the textbook because textbooks don't get published from rough drafts, right? So in other words, maybe one reason I'm doing this is because it's the end of a long road of a lot of trial and error. And that hard work is part of what they mean by genius, not just inspiration from, Mount Sinai. Like, I'm doing this because I'm on a quest to try to make sense of waves. I now have an expression for the second partial derivative with respect to time. I have an independent expression for the second partial derivative with respect to space. I look at these two expressions. I remember that either my professor or my brain said to me, is there any way to relate these things? kind of again, like Gabrielle asked the other day, can you relate omega and K? Can I relate the omega relationship to the K relationship? Well, I think I can by cracky, despite the fact that I just said by cracky, because if I look at them, they're incredibly similar expressions. Each one of these answers basically says blah, blah, blah times cosine of blah, blah, blah. No, it doesn't. It says blee, blee times cosine of blah, blah, where blee, blee differs from the two expressions and blah, blah doesn't. What am I? I'm saying, look, I'll rearrange. It looks like, look first. I'll look at the time one first. If I look at the time one, I can rearrange it and say, I can divide, excuse me, what I'm going to do, I'm going to look at this. Okay, I'm going to start, here I'm pulling a little macho move here, or whatever the spiritual equivalent is. Like, I'm noticing one thing is every time I write cosine and then I open the parentheses, every single time in this entire discussion, whatever's in the parentheses has always been the same. Okay, it's always omega t plus kx. By the way, I could just as easily say minus kx. I know that keeps concerning people whether the phase, but it's all, you could say plus or minus, comes to the same thing. But what I have every single time in the cosine argument is omega t plus or minus kx every single time. So I really actually don't need to get too bogged down in that. The cosine expression every single time is the same. So I'm just going to call it cosine of squiggle for the moment, just so I don't, So the second time derivative was negative y naught omega squared. In other words, this cosine of squiggle. And the second partial space derivative was similarly, if I just rearrange a little bit, negative k squared y naught cosine of squiggle, right? Excuse me. Question. Oh, Cheska, question or no? Or no? Okay. And I'll get chat the question in a second. So in fact, why don't I take each one of these and divide? Like they're each something times a cosine. Let me write even there. In other words, right? So in other words, negative if I just look at the first equation, -1, I think it's fair to say, if I look at the first equation, and divide both sides of the first equation by omega squared, I could say negative y naught cosine of blah, 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 equals this divided by omega squared, right? I'm taking the first equation, dividing both sides by omega squared to just get an expression for negative y naught cosine. And I'm going to do the same thing to the second expression, so I can get two separate expressions for that cosine thing. Right? I'm just trying to relate the two expressions. They both seem to be related to the cosine thing. So I'm isolating the cosine thing and looking at it. So the second thing is negative y naught cosine of b equals, okay, I'm not changing anything, it's all right, but you obviously no one could read this if they're like, depending on, so I'm just recopying. Okay, this is. And this is. Okay, so I got an expression for time derivative, I got an expression for space derivative. They each contained like an identical cosine piece So I rewrote everything and expressed it. I what do you call it? I collected like terms and solved for that cosine piece in each case. So now I have two, I've now rewritten each expression just as a cosine piece equals blah, blah, blah. So cosine piece equals something, but cosine piece also equals something else. So I can set the two equal to each other. And you may have done all this a totally different way, and that's completely fine. If you can see it your way, no problem. But some people can't say this at all on their own. So I'm showing you a way to see where I'm trying to go with this. And nothing's obvious until it is. Nothing is obvious until it is. And then once it is, it seems like it always was. And that's why the word obvious is horrible. So I'm ultimately saying this, thus, nope, not saying that. I'm saying this. All right, according to what we're saying, that since cosine equals some time derivative thing and the cosine piece equals some space derivative thing, then the time derivative thing equals the space derivative thing as written, right? So in the long run, this means thus, what I'm really saying is this, one second, I'm gonna pause for 1 second, in 1 second, but this thing in blue is possibly certainly the most important conclusion I've said all today. It may be one of the bigger things in the last couple of days. And I think you've seen it in lab. I think what I'm hopefully doing right here is from a different way or from a different starting point, trying to land in something that was very big in lab 3, okay? So hopefully you recognize this, but I'm trying to now explain it a different way, or whether or not you recognize it. I'm saying now, but I think I've just derived it. Like, I'm not quoting your lab. I'm independently saying that we just derived a new second order differential equation, one that is called the wave equation. Don't be confused again. That cosine thing was a equation. It was technically, I would call, an equation of motion for waves, just like a cosine omega t is like the equation of motion for a harmonic oscillator. But the differential equation that governs our oscillator is that d2y thing. Well, now we have a new differential equation that looks kind of like our old one, but looks a step more complicated or thicker, right? Because it has derivatives on both sides now. It's a second order partial differential equation, right? So it relates two different derivatives of the same function, but the relationship is a differential equation that I'm ultimately going to say any motion ever that can be described by this, like if you have any three variables, y, t, and x or more, but if you have any set of variables that refer to, like, in a way, anything in space and time, if there can be arranged this way, if you have a phenomenon that can be described by this differential equation, then that phenomenon is wave motion. And conversely, if something looks like a wave, is observed to be, measured to be, analyzed, if data says that something is a wave, then that phenomenon must be describable by this differential equation, the wave equation. In principle, lab 3, you are collecting data to get cosine graphs that ultimately together made for this discovery. In principle, in theory, I'm saying that here. Now, I'm going to show you it a different way in a moment, but I'm going to pause for 1 second. Just let that, but that's the wave equation. Okay, that's the wave equation, and we got it. It's a second order differential equation we got by differentiating twice a function that we think we got from collecting a whole bunch of oscillators and staggering their phases and thereby constructing this wave motion. I'm going to pause for 1 second because I have questions from another part of my life. Hold on just 1 second. Oh, great. Okay, sorry. Yes, they're gone. It's just like yesterday. I mean, in theory, but yes. Oh no, definitely, yes. Sorry. Okay, wait. A couple of good questions. I do want this to sink in because it's big, but there are a couple, and I want to give again. Sometimes it takes a while to think of a question, so I don't want to suggest that just there's only one moment to ask a question, but there are some good ones already. So I am saying, like, to Sophia's question, everybody, so Sophia's question, and thank you for going public with it. So with a partial derivative, we can just ignore the kx portion. Yes, I'm totally saying, as long as you're seeing the whole picture, I am saying the whole thing of partial derivatives is a partial derivative applies to one variable at a time. So yes, big point. If you're taking the partial derivative of a function with respect to t, like if t is in the denominator of the, like, let's look back here a couple pages. Sorry, like here on this page and then on the next page, if I'm taking partial y partial t, if I'm taking derivative with respect to t, then it's not that I ignore the x part, it's that I treat x as a constant. So, I mean, for example, well, I'll be more elaborate about that in a minute, but it's just everything that's not the variable that you're looking at, everything that's not that variable in a partial, you treat as a constant. So it doesn't mean you ignore it, but it does mean like the derivative of a constant is 0. So if a constant is sitting by itself, like kx, then the derivative is 0. I'm not really ignoring it. I'm actually getting like a 0, is coming out from chain rule. Like the chain rule is really omega plus 0, but that's omega, so I didn't write it in. Similarly, then if I take the partial derivative with respect to space, then I treat t as a constant. Right. So let me just do one more quick review of that. Like one thing that might be, I want to make it clear that I'm not ignoring the other variable, but I am treating it as a constant. What I mean by that is, like, say, for example, say we have, okay, a completely different function, just to make a point, because these are good questions. And again, this math is new and I am trying to teach it, so people should be trying to learn it. So yeah, like say I have y equals, say I have, wait, sorry. So y, say we have u equals some function of x and y, like example, say that u of x and y is equal to, like, here's a good one. Say it's equal to 5x squared minus xy. Okay, like that's a legitimate function. That totally could be a function. The x sort of appears in both of the terms and the y only appears in one. Okay, so it's like an interesting function. It's, different it has a different relationship to x from the one it does to y. It's totally like, oh, cool. Oh, cool. All right, I'm still going to continue this answer for anybody. I see that the person who asked this now gets it. Cool. I'm going to finish the answer anyway, just in case other people do. But so say I have this, and this is a good practice exercise for everybody. If I have this, then du dx would equal 10x minus y. And du dy would equal, I probably should have given people time to think about this for a second, but sorry. That's supposed to say du. Okay, partial u partial x would equal 10x minus y, and partial u partial y would equal 0 minus x, i.e. negative x. I'm going to ask everybody to stare at that for a moment. Make sure you get what I just wrote, just as like how you do partials. Because this is the difference between ignoring a term versus, if a term equals 0, it looks like we're ignoring it. So I'm saying that if we're taking partial with respect to x, then we treat y as a constant and vice versa. So okay, that's the best example I could see. But then I had another good question. Someone asked another question in the chat. This one, wait, what? Right, okay, so I think this answers some of the private questions were the same as this. Is it legal to add the questions together? Is it legal to add the equations together? It's totally legal to, yeah, everything I just did to get that whole thing about when I just got the wave equation, I got it one way that makes sense to me, sort of rearranging the terms and dividing, but there's a million ways you can do it. You definitely can add the equations together, or you can divide one equation by the other, absolutely. Any way that you know how to handle two equations, two unknowns or something, as long as you get it, you get it. And if it works out to the same answer, it's mine. Oh, by the way, not by the way, but to really make that clear, what I'm saying so far, our finding of today, so to speak, and again, this is hopefully a find, I'm saying we just arrived, we just found, like, we just found that and by the way, I'm very aware that there was one more private question that I still haven't answered. Great question. Should not have been private. I'm going to answer it in 1 second. I haven't forgotten. I just want to say something first. Okay, this is what I just found. Right now, just to be clear, I found it the way I did, and I'm writing it the way I am for a reason, to show you something. But you just as easily, if this is true, but it's equivalent to say, well, I'll put it on the next page. Like, it's equivalent. The following two things are equivalent. This is what I just wrote. That's a joke. That's a joke. It's not a pun. It's a palindrome. Sorry. But the palindrome of Bolton would be not love. Okay, so we have this. I just wrote this, but I'm saying you could just as easily write this. Right? Like, you see that they're equivalent, right? I could put the t part by itself, or I could put the x part by itself, either way. But one is like dividing by the constant versus the other. So the constant would flip. But either way, you're right, as long as you're consistent, the units all work out. Either one of these is consistent. I prefer the first way for reasons you may see. But either, oh, and go back to page 55. Now, there's still a question that I still have not answered. A great question about, is there a name for this omega squared over, like, so I'm getting omega squared over k squared in there. So there's a good question in the chat of like, is there a name for that? Don't let me forget that. I totally want to answer that. Again, that one totally could have been a public question, but it's such a weirdly reverse critical thing for me to say. Page 55, so page 55 here. Yeah, so this is page 55. What I just wrote was just this again. Like what I just wrote on page 57 was this again, but then in equivalent form. But this is the wave equation. However I write it, this is the wave equation. Okay. Now somebody asked in the chat, somebody asked, like, is there a shorthand or a name or something for this? Which is a great question, because like, in fact, I'm going to sort of hope that I'm holding up page 55 for long enough here. I'm going to go further a page. I'm just going to keep writing the same thing over because it might be the most complicated thing in a way that you've ever seen that's real. Like, it certainly intimidated the crap out of me when I first saw it. So I'm going to keep writing it so we get used to it, but also because I'm analyzing it. So I'm saying we have this. And I want to address what this omega squared k squared thing is. One way I can understand it is like, let's back up for a second and recall, like, let's remember. Like this, okay, what we just got is waves, wave propagation. Like this thing is wave motion. But let's remember, simple harmonic oscillation looked like this, looked like the following. Now let's pause for a second. Simple harmonic motion, our first differential equation, our first second order differential equation. Simple harmonic oscillation said, oh yeah, as long as you got some variable whose second derivative per time is proportional to the variable itself with a negative sign, then we call that simple harmonic oscillation. In other words, as long as the second time derivative of some variable is equal to a negative constant times the variable itself, we said that's Hooke's law generalized. Now, what are we saying here? Well, first of all, our regular derivatives have now sneakily switched to partial derivatives because now we're looking at a more robust function. We're looking at a function of two variables, not one. So our single derivatives, which used to be sufficient, now switch to partial derivatives. Okay, but they're still like derivatives. So with that in mind, like look, like the left side of both of these equations is essentially identical. In fact, truthfully, I could even write the bottom one with partials and it wouldn't be wrong because, you know, it's like there's only one part, so it's still true. But what I'm saying is on the left side, there's a second time derivative with respect to the variable equaling, and now look at the right side, equaling some constant times something. In other words, both equations are saying that the second time derivative, if you like, the acceleration is directly proportional to something about the variable. In the case of SHO, the second time derivative, the acceleration, is directly proportional, times a negative sign, to directly proportional with the original variable. Here in the wave equation, okay, the negative sign is dropped. We'll get into, the negative sign goes away. That's nice and helpful. We don't have to worry about it anymore. I'll tell you what it means soon. But putting aside the negative, we still have second time derivative. Acceleration is directly proportional to something about that dependent variable. Only now, the big difference is now, instead of being, like it used to be directly proportional to the variable, now it's directly proportional to the second derivative of the variable, which is like, whoa, okay, that's a lot, maybe, especially because we might have already thought, wait, I thought I had second derivative on the left side. How's a derivative popping up again on the right side? I will address that. But the very first thing that's really cool that someone is pointing out is like, either way, both times in the equation, we have acceleration is equal to some constant, whether positive or negative, times something. What's in the parentheses, in other words, is a constant. When it was, and it gets squared because the square root, like in the case of SHO, we called that constant omega squared because we ultimately found out that the square root of it, like square root of this thing, is angular frequency. It's like the rate of the oscillator. Well, here in the case of wave, does the square root of the constant mean something? Is basically what somebody's asking me in the chat. Like, can we, since it looks so similar to simple harmonic motion, can we say something about this constant? And the beautiful thing is, thanks to Gabrielle's question yesterday and thanks to our intro today, we totally can. Like, we've already said it. The square root of the constant in oscillation, the square root is straight up omega, the angular frequency. The square root of the constant here in the wave equation like the constant is now omega squared over k squared. So the square root of it is now, it's no longer omega, it's omega over k. But we said, what is that? We spent the first half of today's class proving that that's v. And here's where someone else is, where Ajeta's question comes in also. In other words, Another way that we could write the wave equation is this. V, we said equals omega over k. Like the speed of the wave propagating through space is the number of cycles it makes per time divided by the number of cycles it makes per space. In other words, it's how big a wave length is divided by how much time a wavelength requires. So I'm saying the way, just like in harmonic oscillation, what Hooke's law is ultimately saying is like the acceleration of some particle. If you have some mass on a spring, the rate at which the mass accelerates toward the equilibrium of the spring, the rate at which a mass accelerates towards spring equilibrium position is directly proportional to how far away the mass is from equilibrium position. Right here, here we're saying the rate at which some piece of a wave pulse accelerates back to equilibrium is directly proportional to some derivative thing that I'll address in a minute. But the constant of proportionality, like we're saying this, I guess I'm saying this, I'm saying i.e. for a wave, for a wave at any and all points in space and time. If you're looking at the ocean, the surface of the water in the ocean, and you see wave ripples everywhere, and you're like, wow, wave motion is occurring in this water. Or if you're in a room and you hear me talking, so you're like, oh, sound waves are like happening in this room. And that's the way you have to say it, because you can't say like there is a wave over here. Like if you're like, there's waves, right? Then what it means to say that there are waves, mathematically or rigorously, to say that there's wave motion occurring, if it really is to say that at any and every given point in space and time, like you name any point in space at any point in time, and like if you choose any point in space on the surface of the ocean water at any given time while observing waves, then what you're saying is that for any point in space and time, if you were to graph, like, so you pick a little piece of water, like in the ripples of the ocean, and at some moment in time and space, and you ask the rate at which that piece of water is accelerating down toward the equilibrium, like the flat level, base level of the water, the rate at which it's accelerating down is directly proportional to some other derivative, which I will elaborate in a moment. It's directly proportional to some other derivative, directly proportional meaning the constant. So I'm graphing a derivative as a function of some other derivative. Weird idea, but you will graph whatever you need to graph in order to get straight line functions, basically, as a scientist. The slope of this line, delta over delta, so to speak, equals v squared. Again, I still haven't really explained what's going on that x-axis. It's some kind of derivative. But what I am saying is the relationship between these two derivatives, according to the wave equation, is a constant, right? Like v squared equals omega squared over k squared. And omega and k were both constants fixed by the material in the medium. Remember, right? Omega is a parameter. It is a constant. It's a constant given the material. Like if omega is really coming from literal masses on springs, then omega is like square root of spring stiffness over mass, right? But if we're talking about in the water or something, then it's like the molecular stiffness, like the molecule spring stiffness divided by the molecule mass, right? But whatever omega is, it's based on the materials. And as long as the materials stay constant, then omega stays constant. Same thing, k is based on materials. If the materials stay constant, k is constant. So actually what we're saying here that's very deep and big about waves is I've got this wave equation. I've got this wave equation now that says basically something like a wave motion is like a simple harmonic motion in a way. It's a situation where the individual, oops, sorry. This gets to, it's 3:10, okay. This gets to, again, a question from a couple days ago. I think it was actually Gabrielle's question. Like, what this is really now saying, if you, we started by saying, look, if waves are gonna ripple through from point A to point B, if wave motion is gonna ripple through space from point A to point B, actually what has to happen is there has to be a bunch of stuff between point A and point B. Maybe water molecules, maybe air molecules, maybe the molecules of some long metal spring. But like, if you want to see a ripple go from point A to point B, what you have to have is a bunch of material stuff that all oscillates in a staggered way. So that material stuff like goes up and down. And then what you watch is some disturbance go from, say, left to right, you know, from point A to point B. Like, but in order to see a wave pulse, which is immaterial, you have to have a bunch of material oscillators doing something specific. And that bunch of material oscillators recall the medium. So thus far, what I am implying in all of this is, as far as we can tell so far, analytically, to have a wave, you must have a medium. A medium doesn't slow down a wave. It's not like air, like some people think like, well, sound can pass through air or sound can pass through water, but either way, like sound has to sort of fight the air, and the air like slows down or gets in the way of the sound. It's like, air doesn't get in the way of sound. The motion of air allows for the motion of sound, right? If you're understanding what I'm saying. To have sound go from one place to another, you got to have some bunch of material particles that are all doing this elaborate wave dance, right? But now what I'm saying is one step even further, and light is what challenges that claim. Like, light is ever strange and mysterious, and it isn't ever, like, it's been resolved. But putting aside light, which we have to say more about, any other wave that you've ever heard of has to obey what I'm saying, not because of observation, but because of logic. But now what I'm adding to that truly is staggering to me, is that if you really follow all of this, and if you really believe, if you believe that the chandeliers in the Sistine Chapel oscillate back and forth at a rate in time which does not depend on how they started in space, right? Like, if you really believe that harmonic oscillation means it means, I can't put my finger in the camera. Like, harmonic oscillation means a clock. It means tick tock or tick tock. Like, it means whether you go tick tock or you go tick tock, it's going to take the same time either way. That's what harmonic oscillation means. That the tick tock rate is fixed based on the materials, not how you set them up. Well, same thing here now. We're saying if you believe that, then it turns out that if you set up all these oscillators and drive a pulse through some medium, like have oscillators oscillating along the y-axis such that we observe a pulse propagate along the x-axis, what all of this means is that that pulse will propagate at a given, constant, fixed, unwavering, unaccelerating speed, which we could even predict and know the moment we looked at the medium. Like, you wouldn't even have to send the wave through. If it's a sound wave going through air, once you say, oh, I got a box of air here called a room, at standard temperature and pressure, like I got air here, and it's like air molecules made of nitrogen and yada, yada, and those nitrogens are vibrating at this temperature and this pressure, then you, in effect, have a bunch of little air springs that you know what rate they're all going to vibrate. And thus, if you say, I'm going to now send sound through this air, like I'm going to shout, I'm going to send a compression pulse through this air, we already know in advance what rate each one of those is going to vibrate, therefore what rate the sound is going to propagate through the air, and nothing can change that rate. Not me running while I'm shouting, not me shouting more quickly, nothing. All that can fix the rate of that propagation is the medium itself. That's why people can say stuff like the speed of sound. Like, you don't ever hear people talk about the speed of baseball. A baseball can be thrown at 100 miles an hour. A baseball can be thrown at 30 miles an hour, right? A car can go 60 miles an hour. It goes 80 miles an hour, blah, blah, blah. Planets, things go whatever speed they go. But waves, people can literally say the speed of sound. And what are they talking about? They're talking about what they're really assuming when they say the speed of sound. They mean the speed of sound in air under normal conditions, like standard temperature and pressure. What they're, without realizing what they're tacitly allowed to do that, because sound actually does just travel at a given speed. Oh, go back. Yeah, sorry. Sound travels at a given speed. Sound travels at a given speed that is fixed by the materials of what it's traveling through. And once you fix those materials, you cannot speed up or slow down the sound. You can totally rely on it to go at a constant rate. I'm saying a lot here. So, like, and again, this now goes back to Ajeta's like totally fair question a number of minutes ago. Like, it sounds like I'm contradicting myself. I'm literally saying now the speed of a wave is a constant, all things considered. Like a speed of a water wave through ocean is going to go at one given speed as long as the ocean water is defined to be like there are factors that contribute to what makes a medium. If the medium is more salty, if there's more salt in water, then okay, it's got different material properties, so that can make waves go faster. Or if the depth, if the ocean floor starts sinking, so you're talking about deeper and deeper water, okay, then that's a different medium. So things, you can change the medium to change the speed of a wave, but that's the only way you can change the speed of a wave. That's what we love about waves. Waves automatically, once you send out a wave, it goes at a known, fixed, unwavering speed that's incredibly reliable, more reliable than baseballs, rockets, blah, blah, blah. That's why we send information via waves, because like we can. But what might be confusing to anybody now is I'm saying the speed of a wave is constant because it's omega over k, and omega over k are constants. But you might be saying, wait, I thought you just took these derivatives and you're getting these crazy derivatives with cosines and sines, and like, didn't you just get, aren't you saying the acceleration, aren't you putting it on a graph and saying it's not constant? Right. This goes back to Ajeta's question. Every derivative I just took was examining an individual particle. Like if you're thinking of water waves, for example, got a bunch of water molecules going up and down, thereby creating ripples going across, right? Each water molecule is oscillating up and down with velocities that are continuously changing, accelerations that are continuously changing along the y-axis. And those are the derivatives that we just took and analyzed and set equal to each other. But the net result of all of these continuously smoothly changing velocities and accelerations along one axis then leads to a constancy along the other axis, a constancy that we call propagation, and that is so powerful. So we get things like sound, which always goes at 340 meters per second, given air at standard temperature, pressure, et cetera. Again, none of this fully explains light yet, because light is like its own thing. But any other wave you can ever picture, and by the way, it only doesn't apply to light because it's not clear whether, or it can be not clear whether light is a wave or not. But anything that definitely is a wave, this applies to. Saying a lot, I'm going to say one last thing and then take a breath. Wait. Yeah, what the graph is saying, it is a funny graph. I'm going to try to, that's a fair, I'm going to try to say what the graph is saying one different way now. Then I'm going to take a breath. Like, it's a fair question. Okay, hold on. Okay, wait. So I want to answer this question. What is my graph saying, right? First, I'm going to say this, which doesn't really help, okay? I mean, technically what my graph is trying to show is that to undergo wave motion means that that there's a certain function describing your motion for which one partial derivative happens to be directly proportional or like in lockstep with another partial derivative of that same function. But given that I just taught partial derivatives like 5 minutes ago, there's no reason that that statement actually helps anybody or makes it any more clear. So what does my graph mean? Like technically the answer is what I just wrote, but I don't actually feel that that answers anything. Let me be a little bit, what I really have to explain is there's two different partial derivatives of the same function. Like how are they different? What are they saying? What I'm really trying to say is this. Like, okay, it's saying, let's picture some overall wave motion, like a bunch of ripples on the ocean surface or a bunch of ripples on your long string in lab 3. And again, I always have to say it in a weird way because I can't say picture a wave, right? Like you could have one bump in a long string and that's not wave motion. Or you could even send one bump along. If you just do it once, that's a wave pulse. But wave motion is things going all over and over again cyclically, like not only something going cyclically over and over in time, like oscillators, but if that whole thing is stretched out in space, if you walk in to the ocean while it's bobbing around, waving, so you're like, oh, there's wave motion. What it means to observe wave motion is picture, like take a photograph of those waves in your mind, or take a photograph of the ripples on a piece of string in your mind, or as you did in lab 3. So you take a photograph and you're picturing one moment of this wave, one moment. So like, if you were to superimpose this on graph paper or on axes, as I think you did in lab 3, if you superimpose it, you're picturing like this is the y-axis, this is the x. There's no t here because we're picturing one moment in time, right? If you picture this, and now you picture some little piece, like let's consider this infinitesimal, this tiny piece, okay? What the wave equation is saying and what that graph is trying to say is, if you picture this little spot, that little bit of water that you've selected in your brain from this like large phenomenon of water wave motion, if you picture that little bit of water, oh wait, I'll go back to 65 for a second. Okay, so 65 says I'm picturing one little bit of space and time excerpted from a larger wave phenomenon. Again, sort of in effect what in theory you're trying to do in lab 3, although again I keep saying that I'm not quite sure how lab 3 worked out for you under these conditions, and I should pause to ask you at some point. But anyway, if you picture some little, no problem, thank you. If I picture some little bit of the water whilst wave motion is occurring, then what this equation seems to be saying is, let's look at it piece by piece. Let's look at the left side. It says, if you picture at some moment the second time derivative of y, like the second derivative of y with respect to t. In other words, if I picture the rate at which that little bit is accelerating along the y-axis, right? Because it's partial y, partial t. So if I, but it's second. So I'm not looking at velocity, I'm looking at acceleration because it's a second derivative. If I ask myself, that little bit up there, that is, this little bit right here, that is presumably at the top, it's a crest of the wave, it's going to start falling down, right? And until it's like an equilibrium, it's going to keep falling until it's a trough, and then it's going to go up again. The rate at which this little bit of the hump is falling back toward equilibrium, that rate of acceleration is directly proportional to, directly proportional to, i.e. equal to some constant, happens to be a special constant, but I don't even care for the moment, it's just some constant times this other derivative. Now, what's this other derivative? This other derivative is also a second derivative of y. So it sounds like I'm being redundant or circular or something, but no, this side says second partial derivative of y with respect to x. So this means now not the rate of change of y in time, not the rate of change of velocity, which we call acceleration, but this one's just the rate at which y changes as a function of x, right? Just literally the second derivative according to this graph, like not invoking time at all. Put another way, like we know for any point on this graph, like the first, if I picked any point on this graph and if I asked like, what do I mean by the first derivative? Sorry. If I picked any point on this graph and asked what is the first derivative of y with respect to x, I would mean like, what's the slope of the tangent line to this graph at that point, right? I'm not talking, so on the left side, I was invoking time. So even though I don't see anywhere time on this graph, I know that the rate of change of position with respect to time is called acceleration. So the left side, I'm saying, is acceleration. But the right side, that second derivative is not acceleration. It's rate of change of space on the y-axis with respect to space on the x-axis. Well, the first derivative dy dx, from math class, like is on a graph is read to be like the slope of the tangent line, right? In other words, the steepness of the graph at that point. The second derivative, according to a math class, right? Second derivative of y with respect to x on a graph, it's not necessarily called velocity because no one had necessarily said anything had to do with time. But just like the first derivative of any variable with respect to any other variable is the slope of the tangent line for the graph of those variables, the second derivative, I'm just going to say, does anybody know the word I'm looking for? If first derivative is slope, what's the second derivative from math, from regular calculus? If you're thinking graphs and functions, first derivative is the slope of the curve. What's the second derivative, like in English? Like what does it tell you about the graph of some graph in a math class? If first derivative, close, all right, first derivative tells you the slope of the tangent line. First derivative tells you slope of the tangent line, i.e. steepness of the curve. Second derivative kind of tells you steepness of steepness, like rate at which steepness is changing. And that's called, the rate of change of the slope. And what's that called? That's right. Think of it in terms of shapes. Like a graph with a higher slope is called a steeper graph, right? A graph with a higher first derivative has a higher slope. It's called a steeper graph. A graph or a piece of a graph that has a higher second derivative is called, yes, rate of change of slope. I'm going to wait till someone comes. You think of like in other words, this has a high first derivative. This has a low first derivative. This has a high second derivative. This has a low second derivative. This has a negative second derivative. You know the word I'm looking for here? You do. When someone says it, you'll know what I'm saying. The first derivative is steepness or slope, i.e. rate of change of the graph. Rate of change is like slope of slope, which is called, like, it can be like up or down if it's positive or negative. Like bowls are very bleh, whereas plates are very not bleh. Okay, the word up, yes, thank you. Oh, and it was private. See now, okay, totally right. Someone totally correctly said what I'm looking for, and I'm not gonna say the name because I respect the private, but see, I think the person deserves total public credit for having said this, but concave is the word I was looking for. So please privately congratulate yourself, and I'm not making fun. Oh, okay, all right. So yes, thank you, Erica, for saying concave. Yes, concavity is totally what I'm talking about. Like, and I want to stress it, like slope of a graph is derivative, concavity of a graph is second derivative. Now I can make a graph of y versus t, right? And so the second derivative of that would be concavity. But I'm saying, like, any graph I have, the first derivative is slope, second derivative is concavity. In this case, if I picture a y versus x graph, right? If I take a photograph of a wave, so I picture one particular moment in time for an entire wave, like I could have done the reverse. I could pick a section of the wave and watch as water molecules go up and down. Again, that's half of what you did in lab 3 in effect. Again, maybe you did none of that and I'm totally lying because I have no idea, so I'll stop saying it. But if you do the reverse, if you take a photograph, hold time constant, and you just look at, oh, how is the uppy downy of this wave varying as a function of ovary? How is rise varying as a function of one, right? So if you look at this and you're looking at this and you pick some point and you're like, I'm like wondering about that point there, and someone just came in, sorry. Then whereas, oops, sorry. Whereas what we're actually saying is that if I pick some point on the wave, some piece of the water which is rippling, and I ask, at what rate is that little, like, I know everything's going up and down, and I know that that piece is like away from the equilibrium orientation, like the flat baseline of the water, where if there was no ripples, where all the water would be, right? Any piece of water that's above that baseline, any crest of wave, I know it's going to start accelerating down toward the flat because everything is going up and down. The rate at which it's going to accelerate along the y-axis back toward the equilibrium axis, which we are calling x, the rate at which that happens apparently is directly proportional to the concavity of this graph at that point, which actually means this. It's like so correct, I think you'll find once I say it. I'm saying that to be in wave motion means that for any given piece you look at any given time, if it's proper wave motion, any given piece you look at will right at that moment be accelerating back home at a rate that is directly proportional to how concave, how not flat, how bent or misshapen or distorted or rounded or warped, however you want to say it. The greater, in other words, the more unflat some piece of a wave is, the more that piece of the wave is warped, distorted away from flatness, the faster rate at which that piece will accelerate back to flatness. It's like saying that there's a restoring force trying to restore everything to flatness, and the farther away some piece is from flatness, the quicker it'll accelerate back to flatness. If that is true at any and every given point in space and time for some complicated motion, then that complicated motion is wave motion. I'm going to say it one more time. I'm saying, and because this is really powerful to me, honestly, I'm saying like, compared to compared to right, what I just wrote is a simple harmonic oscillator. I'm trying to emphasize right now, I'm not bogged down on what the constant is, and also, again, I don't get too disturbed about the fact that there's a negative sign here, like, or whether there isn't. Like, harmonic oscillation meant okay? Remember, for a mass on a spring, for any oscillator, going back and forth in one dimension, right? There's some place called the equilibrium place. There's some position called x equals 0, like a position that refers to, where the end of the spring would be if nothing were happening to that spring, the relaxed, balanced forces orientation for that spring, right? So equilibrium refers to a place, a point, a dot of 0 dimensions. By the way, remember, 1 dimension is a line, 2 dimensions is like a plane, 3 dimensions is a cube or a solid or a sphere, whatever, right? 0 dimension, a line is 1-dimensional, a point is 0-dimensional. For a spring mass system, we believe that there is an equilibrium place, a 0-dimensional location toward which the 0-dimensional point mass is forever accelerating, like it's always being pulled toward the equilibrium position, then it gets there and then it passes to the other side, and there's this mass point that's always being pulled towards an equilibrium spot, and that mass point is free to oscillate back and forth along the 1-dimensional line segment containing that point, right? In an oscillator system, you have a 0-dimensional point mass going back and forth along one axis, one line, forever sort of being pulled toward, accelerating toward a 0-dimensional equilibrium spot. That's harmonic oscillation. Now what we're saying is for waves, we have something so similar, yet extrapolated to one more dimension of space. What we have now here is constant. I don't care what the constant is for the moment. Constant. Oh, sorry, I mean to say, yeah, this. Okay. Now we have a situation where for a wave, even in the simplest case, even in your ripples that were going back and forth along 1-dimensional string, right? The simplest case of a wave, we need at least 1 dimension of space for the wave to propagate, and we need a dimension of time. Like, so the simplest case of a wave is ripples going back and forth through a 1-dimensional medium, like a piece of string, like you in theory have in lab 3. Well, in that case, what is equilibrium now? In the case of a wave, actually, I don't even know, I don't want to draw that graph yet. Sorry, forget that graph. But in the case of a wave, equilibrium is now a 1-dimensional axis or line or orientation. I mean, if you have your string in lab 3, this long slinky, before you do anything to it, it has an equilibrium orientation, and you start making pop up, make a little hump over here, and the whole idea is that the hump falls down, and then another, there's an equilibrium to which everything is constantly in motion, and just like harmonic oscillation, but when you send waves, even in the simplest case, along some spring, what I'm trying to say right now is equilibrium is no longer one spot. Equilibrium is not a location that a mass is trying to get to. Now, equilibrium is an orientation. It's an axis. All the ripples are trying to get back to flatness. Like the way that spring wants to be in lab 3 is it wants to be flat. And every piece of it that you perturb, if you pull up the string a little, what you find is that piece wants to fall down, but then it takes up a bit of the spring, so then the spring gets bunched over here, so then that falls up, blah, blah, blah. But everything is trying to fall or restore back, not to some particular place. Like the spring doesn't care if you and your partner hold it up at 4 feet or you hold it at 3 feet from the ground. It's not a position which defines equilibrium. Now, it's a whole line. It's that everything is trying to fall toward the whole x-axis, right? So what we're saying now is instead of with springs, with oscillators, the farther away sorry, let me go back here. With an oscillator, you have some mass point that can be displaced along a y-axis from an equilibrium point. And we find that in a mass spring system, what it means to be springy, what it means to be elastic is that the farther away along a 1-dimensional line, the farther away you are displaced along a 1-dimensional line from the zero-dimensional point called equilibrium, called home. The farther away you are from home, the faster you accelerate toward home. That's what Hooke's law really, really means. That's the differential equation we're like freaking out about for where I am for months. Oscillation means the farther away you are from the point called home, the faster you accelerate toward home. Okay, waves, just take that concept and add a spatial dimension to it. They say, with a wave, we say we've got now an equilibrium line, and the more some piece of that line is bent away from the line, the more concave some piece is at a given point, the more distorted or unflat or rounded some piece of that string is, then the faster that piece will accelerate back toward flatness. It's exactly like Hooke's law. It is restoration. It is harmonic oscillation, but in time and space. That's what we're saying. So acceleration used to be directly proportional to dependent variable. Now acceleration is directly proportional to concavity of variable. That's what that graph was trying to say, for whatever it's worth. And that's truly what it means to be in wave motion. Waves are there in front of you if, for at any given point in time and space you pick, if you can satisfy yourself that the rate at which some bent piece of the medium is accelerating back toward unbentness, if that acceleration rate is directly, simply, linearly proportional to, determined by how bent we are, then that's wave motion. It's harmonic oscillation in time and space, which I think is very cool. One last thing, and actually, we might even end a little bit early today, just as because you still have this exam and blah, blah, blah. So you don't need, so wait, but there is one more thing to tie it up, I have to say. Oh, right. And what makes, so we wrote down this wave equation. So I'm saying again, in sum, okay, in sum. One harmonic oscillator is this. Okay, that's a harmonic oscillator, right? Rate at which thing accelerates toward home place is directly proportional to displacement from home place. Like that's what that means, right? And the solution to it is this. Okay, this is one oscillator. And again, it's just really truly one oscillator, then maybe phi can almost always be set equal to 0. But to be careful, if you have one oscillator, then the differential equation that describes it is this. And the solution to that differential equation is the cosine thing underneath. Again, and of course, that this is everything I'm saying right here is about the exam that you're in the middle of taking, right? So hopefully it's helping a little bit or something. Oh, sorry. So this is the diff EQ, and this is the solution. That's harmonic oscillation. But we're now saying if you have a collection of oscillators that are properly staggered in phase. So if one harmonic oscillator is something that moves in a highly patterned motion, then if you arrange all these patterned motions, if you arrange all these motions that are patterned in time, if you arrange them all in a very particular and identical pattern in space, then what you'll have is a collection of staggered oscillators, or in other words, a propagating wave pulse. And we say, for that one, I just want to make sure I'm consistent with the, yeah. So if we have a collection of staggered oscillators, or in other words, wave motion, if you have that, then what we're saying is the differential equation is this. Right, similar, but one step more complicated than oscillators. The differential equation is that, and the solution is this. Now, in fact, in the case of the oscillator, we started by deriving the differential equation from basic physics principles, and then we worked our minds to try to get a solution. In this case with waves thus far, what we did was the opposite. We collected data in the lab and found something that looked like a solution, so to speak, an equation of motion, and then we differentiated it twice to get the differential equation. So we're going in the opposite order here, fine. And it turns out you can go in any order on any of them. That's why we believe all of this. But in this case, for a wave, this is the diffie-q now, and this is the solution. And notice that for the last 20 minutes, what I've been trying to make sense of is how this direct, in each case, it's a second time derivative is directly proportional to something. So that means in each case, it's second time derivative equals a constant times something. And in the last 20 minutes, what I'm trying to stress is what that relationship ends up meaning. Like the fact that it's directly proportional in the case of a wave means that acceleration is directly proportional to concavity. I mean, in short, that literally the summary of everything I'm saying for 20 minutes is for a wave, acceleration is directly proportional to concavity. But, you know, really for that sentence to make sense, you kind of have to say acceleration here at this point is directly proportional to concavity here at this point, blah, blah, blah. But that is what I'm saying. But notice I can make all that. I could say acceleration is directly proportional to concavity, i.e. acceleration is equal to some constant times concavity. If you really get what I'm saying, that's already kind of a big point. Like that wave is like harmonic oscillation in space and time. Acceleration is directly proportional to concavity. But also, at the same time, I'm saying that constant itself, the constant of proportionality, is not only constant, not only just fixed by the material properties of the medium, but in fact, that constant is the rate at which the whole freaking wave will propagate through the x-axis. So this wave equation, and this is where we're going to stop. I mean, I'll take questions, but I'm not going to introduce anything more today. But this wave equation, which really is not, like, is impossible to make any sense of unless you've had some practice first with the harmonic oscillation equation, you know, on which it was based. But once you sort of get used to that and you start looking at this with less fear, if that applies, when I say this, oops, sorry. Well, when I say this, or in other words, like this whole last 20 minutes, I've just been treating the piece in the parentheses as just any constant that was a constant, but didn't have to have significance necessarily, it was just a constant. But I also, in the first 20 minutes, was trying to address people's questions and point out that that constant actually, you know, really does mean something about the wave. You know, I just think maybe this will make it clear to people too. I've never done this before, but maybe if you want, you could put a little sub X on the V, if that makes it clearer. Like the V that I'm talking about here is V along the X axis, the way at least we're setting all this up. Like not V along the Y axis, but V along the X. Do or do not include that X if you like. But whatever you do, note that this whole thing is constant wave speed. That means that this one equation contains a heck of a lot of information being all related to. It's saying second derivatives of vertical position with respect to time are equal to a constant speed along an x-axis times second derivative with respect to x of, I mean, I can't even say it in English, but almost every aspect of any wave motion you would want to study is all packed into this one equation, which on the one hand, I'm trying to say this equation is so simple in a way. This equation is just saying that this chunk, if you were to graph it as a function of this chunk, you would get a straight line whose slope is propagation speed squared, right? In a way, it's really, really simple. I'm just saying one thing is directly proportional to another, except that the things, the pieces, the clumps that I'm putting on the y-axis and x-axis, you might not use, oh, and they're wrong too, sorry, so this is supposed to be a 2 right here. Like you may not think of derivatives as things that you can put on axis, but they are functions like any other function, or they're variables like any other variable. So this equation, the wave equation, is like F equals ma. It's just saying a second derivative is directly proportional to some other. I mean, it's just saying something is directly proportional to something else. It's just that the things, the pieces, are second partial derivatives. So you got to have some knowledge and thought under your belt before you can even see the simplicity of this. But it's a simple relationship between two complicated chunks, I guess, is what I'm saying. So it does take getting used to, but it is a fabulous, in my opinion, package of characteristics and parameters to describe one phenomenon at once. And the ultimate point, what's the ultimate takeaway of all of this? Like, takeaway. The big takeaway, which again, I don't know if it sounds obvious or not, but the big takeaway of all of this is that if you allow ripples to propagate through some medium, if you allow ripples to travel through some collection of particles, they will ripple through that medium at one fixed speed, one constant unaccelerated speed, as long as the collection of particles is fixed. Like, so if it's air molecules at a certain temperature, at a certain pressure, if it's water molecules at a certain depth, at a certain temperature, if it's metal coils at some constant stiffness and with some constant mass, then there's one and only one way to send ripples through the medium. And so whenever you see this in a textbook, which could also be written, oh no, it can't be written like that. I mean, it could, but it'd be wrong. Or this, however you write it, but it's usually written in the top way. Like, it's like F equals ma, right? It's like it's like a linear equation. If you say the speed of a wave equals its wavelength times its frequency, like, that's totally true. But what's actually powerful about it is that, what's powerful about it is that for any given wave, the left side is fixed, right? So what it really means is you send ripples along, you hold one end of a long metal slinky, and your lab partner holds the other end of that slinky, and you want to send ripples to your partner. Or if you're like in the bathtub and you like take your finger and go like this to the surface of the water, so you send ripples out from your finger on the surface of the water. Of course, in both cases, in any case of making a wave, you can make your finger go like really rapidly. You can send pulses to your partner by shaking the spring really, really rapidly. You could send a lot of ripples per second to your partner, or you could send very few. You can adjust the frequency with which you send ripples to, you can adjust the frequency to your own liking for any wave that you send through any medium. But by doing that, all you're doing is configuring how many ripples you send per second. You can send ripples rapidly to your partner by shaking a lot, or you could send very few ripples per second to your partner. But what you can't do is change the speed of a ripple. Only the material properties of the medium can do that. So if you make a lot of ripples per second, necessarily the length of each of those ripples will be very small. If you make less and less frequent interval ripples, then the size of each ripple will be very big. In other words, yes, it's mathematically obvious. I'm saying if V equals lambda F, nothing's obvious, but yes, it's mathematically straightforward that if V equals lambda F, I'm just saying that F is inversely proportional to lambda. But here's the non-obvious part of that, the part where people get fooled if I just say that. I could also say that F is directly proportional to V. I mean, the thing is, I know looking at, and this is, I swear where I'm going to end. If I say V equals lambda F, I was trying to let you go early, I apologize. If I say V equals lambda F, yes, I think it's straightforward to people that if F goes up, lambda goes down, assuming V is held fixed. It's equally obvious, maybe, that if you don't hold V, if you hold lambda fixed, right, then if F goes up, V would go up. Like F and V are directly proportional, assuming lambda's constant. Lambda and V are directly proportional, assuming F is constant. If you hold any one constant, then the relationship between the other two is whatever it is, right? So if I just wrote that down and I said, what would happen if you tweak F? It's actually not fair to just go, oh, obviously, sorry, let me say this again. If I just write down V equals lambda F, and I then say to you, okay, so what would happen if I make F bigger? What would happen if I double F? You might think, well, it's obvious, lambda goes down by a factor of 2. But someone else could just as easily say, well, if you double F, then V is going to go up by a factor of 2. If you double F, then if someone would say if you increase F, then V would increase. Someone else might say, well, if you increase F, lambda will decrease. They would both be right in principle from math, but I'm saying from physics, we actually know that the thing that can't change is V. So then this equation becomes very straightforward and powerful. V for a wave is fixed. Therefore, if F goes up, lambda goes down, and vice versa. And that's all you can do to a wave. You can make the frequency of a wave bigger, and you can make more ripples per second, each of which is a smaller ripple, or you can make fewer ripples, or you can make bigger ripples, and at the expense of having fewer of them per second. But no matter what you do, each ripple will go across the medium at one and only one speed, which is fixed from the start, and which is the constant in the wave equation, this. Right, this. So that's when I'm going to end there for the moment. Everything I just said, I hope, anything I said, I hope is helpful and you can use in your lab stuff. Most of it directly is not on the exam you're working on right now. It would apply to future homework and stuff like that. You're not going to get more homework or anything between today and Friday. Just work on the exam. You might get more homework over the weekend. I will stay here for a couple minutes and answer any questions that are now. I just want to give a pause, a beat though. Anybody can leave now. Like I'm done. I don't want you to be late for lab or whatever. You can go now, but I'll also stay for a few minutes for questions. So I'm just going to hold it so don't ask the questions yet. Let's just hold it. You can leave, and then I will. Right, I'm going to look at the chat also. So let me just look at the chat. Oh, great. Okay, wait. Okay, couple questions. I am going to stay for a couple of questions. And I just looked through the questions. I'm going to answer them, but one of them is about the exam, and it's a fair question. So if anybody's still here, let me answer this super quick. And if not, tell your friends. Someone, very fair question. Someone asked privately, on the midterm in part 1, I give this base differential equation, and it says something about, this is a great question. I was wondering if someone might ask this. In the thing, I say like negative KQ over R cubed times X equals like something. And a very fair question is it a typo? Did I forget to put a squared on the KQ over R cubed? I don't know how to say it more clearly, but it's a very fair question. Like on part 1, I have this function where I put KQ over R in parentheses, and someone is asking whether it's possible that as a typo, I left off the exponent 2. That is a great question because it totally, only someone who knows what's going on would even ask that, first of all. Second of all, it's totally possible that I would make a mistake like that, so it's not rude at all. It happens to be the case that I looked really hard at that question. It's not a mistake, but I was worried that it would look like a mistake. So there's somewhere else in the question where I tried to do something to emphasize that's actually not a mistake. It is intentional. I'm not trying to trick you, but I am trying to be challenging. It's not a mistake. I didn't leave off the 2. Take it that way. So it's a fair question. Let me also say about that, because I can make mistakes. So anywhere in an exam, you're allowed to ask me questions like that. It's just we're running out of time. But like that's a fair question no matter what. And if someone sent it to me in an email or something and I caught it, I would answer it to everybody. But I just might not catch it. So let me say, anywhere else in the exam, if any of you are looking and you get to some place where you're like, huh, I totally think I would know how to, like this question, I think it's really trying to ask something else, but I'm not sure. When in doubt, the best thing to do is answer the question literally as it's being asked, even if you suspect I made a mistake, and you might be right. The best thing to do is literally ask a question as it's asked, but then you can make a sidebar note like, however, I think this question might mean this, in which case, blah, blah, blah. Okay, in other words, do what Google does. When you type in a search thing and you make a mistake when you're typing, like you're trying to write Yaverbaum, but you write like Javerbaum or something. So Google like says, okay, we're gonna take you literally and search for Javerbaum, but are you sure you didn't mean Yaverbaum? You can totally do that to me on an exam. When in doubt, answer the question exactly as it is, because if it turns out that I did make a mistake, I can't punish you for that. So the first way I grade everything is like based on what it actually says on the paper. I don't want you to have to read my mind. But so answer it as it actually says, and then you can always make a sidebar that says, however, I think just in case, blah, blah. And believe me, you'll take all the money home if you do that. Again, it's not being rude. You're covering all your bases. At worst, if I think I didn't make a mistake, I just won't look at the other, I'll just be impressed, but I won't grade it. You can do that. But yeah, take me literally if you have to. So that's that. Oh, and another good question. Perfect. And I think I remember this. Someone privately just asked, like at the end of like the math bit or the first bit of the test, I gave you like a derivative and then asked you to solve for the function. And it's very reasonable to think, oh, I think Yaverbaum made a mistake. I think he actually meant to ask for the second derivative because that's what he's obsessing through all the other. I actually didn't. I only asked for the first derivative because I'm trying to ask them the other that I don't want to make unnecessarily hard, to be frank. I'm just trying to review. I'm trying to make, I could see how you would think that's a mistake, but I'm actually only asking for the first derivative, I promise. Again, if it turned out that I meant the second derivative, but you literally answered what I asked and you did the first derivative, I can't punish you for that. So when in doubt, if you can, answer what I'm asking, especially if you think it makes it easier than what you would expect. If what I'm asking makes it harder, last thing too. Say I ask something, you think it might be a typo, and you kind of wish it's a typo, because if it's a typo, you totally know what to do. But if it's not a typo, you're not sure. Still do the same strategy. Give me what you got for the easier version. That's still going to be very relevant, very helpful, and get a lot of points. If at worst, I meant something harder than you can do and you can't complete it because it's harder, okay, but you still got all the credit for the easier interpretation. And then maybe if I did make a mistake, you're 100% right. So these are great. I could easily have made a mistake in those two, but I don't think I actually did, if I remember correctly. If you have any, yeah, all right. So it's really fair. I'm also getting a very fair, and I see why this is private, a very fair question of like, if you try to ask me questions in email and I don't get back to you, sort of what should you do? Well, the honest answer is I'm not actually asking you to call my number. And that won't actually make it better, because if everybody did that, then I wouldn't answer my phone either. It is true for any one of you. This is how I deal with my phone number. Any one of you that I am writing a recommendation for or anything, which all of you are welcome to ask me when we're done, anybody that I have to do something for their life. If you ask me for a recommendation and I say yes, which I'm sure I would with many of you, and then I owe you a recommendation and you have deadlines, then I give you my phone number and we use that to make sure I don't blow any deadlines. But for the whole class thing, I'd rather not have people use my phone number, because honestly, then everybody would, and then it would jam up, then I wouldn't answer that either, and it would self-defeat. Try to get me by email, but it's true that I can be very bad about that. I do suggest first, the first best thing is try to email me through Google Classroom. I will, don't use my regular email address. Just send me a question through Google Classroom that will go to my Yaverbaum at JJ Physics. In other words, send a question through that, because that's only for you guys, and that I don't mind looking at. So first,
Professor,
yes.
very quickly, I just have a question, if you don't mind answering about the test, a quick one.
Yes, let me just finish this answer super quick, which is this bottom line. I will, so try to reach me through email through the Google Classroom, but I know that can get bad because I'm bad. So the last thing to everybody is, what I'm going to try to do is send you all an announcement in the stream about how I'll try to set up some office hours or something Friday morning or something way before for last minute questions, or I'll try to do that and send. But basically, unfortunately, there's nothing better than for you guys to try to email me. And I will try to, email me through Google Classroom and I'll try to check. But okay, go, Antonio or Anthony, go.
Yeah, I was just gonna ask, so on the test, I think it's question, hold up, I can bring it up. I think it's, yeah, so question 1B. Yeah, for the first part, the math question, part B, it says dx dt is equal to negative omega squared x. Is this supposed to say d2x over dt squared, like the second derivative, or is
Right. I think that was a question very fair question, because I would think that that's a mistake too, based if I were you looking. But actually,
yeah.
no, I'm trying to. In fact, this is meant to just review the thing that you did in front of everybody that first day. Like, I'm just.
Oh, okay, yeah.
Oh, you got me. Okay.
Yeah,
Is
no,
that
I was just wondering because I'm like, oh, but that'll be like the natural log answer. I'm not sure if he wants that one or not. Okay, thank you. Thank you,
Yeah,
Professor.
no, thank you. Perfect. No, got it. Perfect. Yeah. I can't say if that answer's right or right, but yeah, you got it. You got it.
Yeah.
Yeah. Cool. All right. Oh, wait, sorry. Tell me again where you go to. Oh, you go to Rensselaer Polytechnic.
Yeah,
Right.
Rensselaer,
Yeah. Awesome.
up
Yeah.
in, up
Awesome.
by
All right. I
Albany.
want to hear. Yes, I'll have to hear about that more later. But yes, I totally remember. That's great. All right. Cool. Good
I have
question.
a question.
Yes. Go. Yes.
I
sent it in a private chat as well. It was in regard to the review sheet. You had posted an answer in the review sheet for question 2, part 4, but you posted the wrong answer in there. And I'm not sure if it's the wrong answer, but it asked for the speed and you just gave theta.
Oh, yeah, that would be a mistake. I'm sorry. Okay. So good point. I'll try to remember to literally send around a proper solution to that. You're right. That's a mistake. I should send you, but I could also tell you right now, how do you get that? Sorry, what?
Because it would be very helpful and it would because we're not sure how to do that part exactly.
Okay, so the way to do that part, if I could just say this right now, if you can forgive me, I'll say it right now. I'm a little worried about starting to write it down, but I'll say this and tell me if it makes. The way you would do that thing in the practice test is, if you already know it's a harmonic oscillator, so you know like d2 theta dt squared equals negative omega squared theta, right? Like you have this second order differential equation where the variable is theta, right? So what I think in some earlier part of the question, what you can write down, maybe I can write this down. Hang on a second. Stop me if I'm thinking the wrong thing, but like if you're given pendulum, and I'm taking from the way you're asking, I'm taking that many of you have discussed this so good, you can pass this word on to others. I'm saying if we're assuming something like, if we're saying something like this for a pendulum, right? So it's like a harmonic oscillator, but theta is the variable instead of x, right? If we believe that, then we know that this is true. And this relates to a question you asked today in class, actually. Like something like this is true. And I don't think there's any reason not to call that theta 0. Like I don't think theta is like a big issue in this problem. So this is true. If it's truly harmonically oscillating in theta, which I think you prove at some point in the problem, then this is true. Therefore, the speed that therefore, sorry. Therefore, we have this with me so far. And this is actually very related to what you asked in class. Like the first derivative of that would be this. Now, the first derivative of this is the rate of change of angular position per time, right? And we know angle by definition equals like arc length or like distance along the arc per radius. Like by definition, where you are in an angle, an angle is a section of a circle. So how big of an angle you make really is like how much arc length you sweep out per radius, right? So in other words, or I could say S or I could say X, like any variable I want for actual position along in space, like meters as opposed to radians, a radian equals like a meter of arc length per meter of radius. So that means like x or arc length, whatever, x equals theta times r, right? So dx, so we're looking for velocity, speed here. We don't have it yet. We have first derivative of theta, but what we want speed, i.e. derivative of x with respect to t. We don't have that quite yet. We have derivative of theta with respect to t, but we know that x is the same thing as theta times r, like if we believe what I just said here. I'm going to flip the page for a second, but I'll flip right back if you want. We want v equals, so we want v equals dx dt, which is the same thing as d dt of theta times r, right? The time derivative of theta times r. I'm going fast. I'm going to say this, and then you'll tell me if it makes sense or not. But I just want to like spit it out. So we want dx dt, which is just we want d dt of x, which is to say that we want d dt of theta r. Okay. R is a constant, so it can come out. In other words, v equals r times d theta dt. Okay, so and r, what do I mean? R equals radius of whatever the circle is, which equals length of string in this case. Like we've got this mass on this string. Okay, so what I'm saying, it looks like a lot, but really what I'm saying is, and I'll go back, I will flip the page back. I just, again, I want to write this. I'm saying, therefore, that v, the thing that we want, is equal to d dt of x, which is equal to so v equals r d theta dt, so it equals r times this, so negative r, the v that you're looking for equals negative r theta naught omega sine omega t, and like t for that question is 1 second, or what, I don't remember what t is capital T over 4 or something, but basically I'm saying you have all the numbers to plug in. This is how you do it. You take the derivative of theta, multiply by r, and that's the expression you need for v, and plug in all the values. Does that make, should I go back to the other page?
Copied it all as you were saying. That clarified everything.
Oh, really?
Yeah. Because I do it because the way I kept referring to it in through the answer key was, I was like, okay, maybe I have to find the radians first, and then you started introducing the new formula in class, so that's why I was asking in class if that would be applicable. Let's say if I had something else, then I was just assuming I could plug it into a different equation, but I was like, we don't pay for here, so that can't work. Got it.
That makes total sense. I got you. And that makes, I appreciate that. And it was a good question in class in any, but so now this does, and you're right, totally my bad for putting the wrong solution in it. So I hope you do pass this to other people if they're, but it does make sense to you, like you'll be able to explain it to other people if they have. Oh, great. I think I'm losing audio. And by the, sorry, where do you go to school?
I go to Fordham.
Oh, right. You told me that. I remember that now. Okay, great. Awesome. Well, I'm very glad to have you. Good. That's a very good question. All your questions are good. Anybody? So that I'm taking. Does that mean that you guys are? If those are your biggest problems, it seems like you're doing okay. I mean, I don't mean to, but it seems like you're in good shape. So that's great because those are totally legit questions. Anybody? Are we good? Anybody else? Blah, blah, okay. Oh, waiting room. I hope. All right. Well, I guess I'm going to go. If that's cool, I'm going to go. I will try to reach out and have some sort of office hours Friday. I can't 100% promise, but I will check the emails and stuff. And you guys are rocking. And
I'm not sure if you can hear me. Is it going in and out, or can you not hear me?
It's going. I think I'm down to one ear that's going in. I can't hear you now. I think it's about to run out. So, but go for it. I can hear you right now. Yes.
Okay. So when we're doing dot and cross products.
Yes.
To just write out, like, let's say we have something that's A dot B. Would you just write out that A dot B equals AB cosine theta, and then on the next line we could just say like AX BX plus AY BY plus AZ BZ, or do you want us to write out like all of the givens where J hat dot J hat equals 1, K hat dot K hat equals 1, and etc.?
Right, great question, totally fair. And very fair, because it seems like I'm the kind of guy who would want you to do all the second thing you just said. And if this were a strict math class, I would. But no, it's fine to do the first thing you said. Like with dot products, if you just literally write the AB cosine theta thing, and then if you've remembered or you understand the AX BX thing, yes, you could just totally write it. And same thing for cross products. Honestly, between you and me, the reason I teach the whole derivation is I think with cross products, people who just try to memorize it and don't get, like, always mess up the memorization. It's really hard to memorize the cross product thing unless you can break it down in your mind once or twice. But right, I'm not asking you to do the whole breakdown thing on the test. Like, you can start from what you said, like, if that makes sense.
Okay, and then if we were writing that down, would that just, like, if we just wrote like A dot B equals AB cosine theta, obviously where the dot on the left side of the equation side, A and B had the arrows on top to indicate vectors. If we just wrote that, would that be considered our given?
Yeah,
just because
yes,
I know.
Sorry, go on.
I was saying, just because I know, like, there's a certain amount of points that are usually allocated towards like givens and making sure we have everything written down. So that's why I was just wondering what you would consider a given to be for a dot or a cross product.
Yeah, no, that's a great question. And the bottom line is, right, I do agree that if you write down A vector dot B vector equals, like, triple equal sign equals AB cos theta, and that would be a sufficient given. I mean, assuming that you then go from that and say, like, equals AX BX plus, AY BY plus AZ, like, somewhere you have to write that part, because otherwise you're not going to be able to fill in any numbers. But yes, I do agree that the AX BX thing follows directly from the given that you just said, and you don't have to write any other givens. I totally agree. And you're right, you do get points for like a given that you write down. So the ones you just picked here are correct. I would say if you ever get in doubt, if like a new situation comes up in the exam and you can't ask me, the thing that you always want, as long as something is a definition, then you can count it as a given. Like, the reason I'm accepting, or the reason I want you to write those things down first, the reason you can't break them down any further, or I can't expect you to, is they're just how we define the dot product. So it's the long way of saying totally yes. You're right to be concerned. Some places I can be much more picky about this. I'm not as picky here because, again, it's a little bit more of a mathy thing than a physics thing. So, but if you write down A vector dot B vector E triple equal sign equals AB cos theta, and therefore E equals AX BX plus AY BY plus AZ BZ, you're totally good. And last piece of advice, the more times you see yourself putting a triple equal sign at the beginning of the problem, the more you're probably doing things awesome. Like, the more you can start any bit of work with some kind of triple equal sign, I think that you're really doing what at least I'm asking for. And that is what you're saying here. Those are the triple, yeah, okay, cool.
See it in the chat right there, but I sent you a picture just to say, like, that's the right layout that you would want a question like this to be.
Let me see that. Yeah, I saw that you did that. I didn't see the picture. Hold on, let me look if I can quickly before I lose a speed review. Okay, I'm opening it. It's coming. Oh, I see it. Wait, so the speed review sheet, you're asking me if that is the correct way to do the the thing that we were just talking about?
Yeah, I'm not asking about the answers. I'm asking more so about, like, the layout, if that's how you would want me to, like.
Oh, yeah. Yes, the layout is good. Yes.
Okay.
Cool. Okay. Sorry. Okay. Oh. Okay. Sorry. 1 second. Sorry. Just. Okay. Yeah. No. So yes. The answer is yes. And is that, I'm getting slightly distracted because I know my audio is falling apart. But are we good? Is that helpful? Does that work?
Yeah, that was very helpful. Thank you so much.
Thank you so much. Awesome. All right. Good. May the force be with you. I'll see you soon. Okay.